I will talk today about how to identify the riskiest components from multivariate heavy-tailed data. And this talk is based on a paper which is part of my PhD thesis, and it's in joint work with my PhD supervisor, Jaakko Lehtomaa. So, at first I will briefly introduce heavy-tailed risks and tell you how to model multivariate heavy-tailed risks. And then I will move on to the more theoretical part of the paper. And this paper, or this thing is it's like, I did my PhD in advanced mathematics, so it's maybe a bit more mathematics and not so much applied, but I hope you can still follow the talk. But I will introduce the minimal set of riskiest directions, and then we'll move on to the main results and also introduce what is these testing sets that we use to find these minimal set of riskiest directions. And in the second part of the paper, I will then show some examples. So we made a simulation study, and then we compared different Pareto tails to each other. And we also made one example with real data. Yes, but let's start with what are heavy-tailed risks. So, for example, in insurance, we would have insurance contracts which are kind of risks, and in finance, some shared prices. But heavy-tailed means that, roughly speaking, that rare events with large outcome have a relatively large probability. So if we look at tail probability, which would be in the picture from some point onwards, what is the probability that this exceeds this level, then here we see the orange graph has a much higher tail, or a much fatter tail than this blue graph. And the blue graph is a normal distribution, so it's a light tail distribution, but then the orange one is this heavy tail distribution. So we're interested in these kind of distributions. So if we would take as an example, for example, the population of Australia, and we would look at the height of the people, then we would see that everybody is about the same size if we're looking at adults. So there's not that much there's no tail events that someone would be 10 times as large as someone else. But then if we would look at the same people and at their yearly net income, then I'm sure that there are people who earn 10 times more than someone else. So this is an example of a heavy-tailed distribution. And examples of events that can cause these heavy-tailed risks are, for example, are natural catastrophes, or then pandemics, or of course also if stock market crashes, then we will see these heavy-tailed risks. So let's move on to the multivariate heavy-tailed risks. So usually insurance companies, they don't offer only one kind of contract, but several ones, so they operate in different lines of businesses. So we can think of each line of business would be one dimension. Same is for returns of multiple assets. If we have a portfolio, then we can have every asset in one dimension, and that's why we are interested in these multivariate heavy-tailed risks. Because we are not only interested in how risky is this whole thing, but we are also interested in where does these heavy tails lie. So can we somehow find some reinsurance strategy or hedging strategy to avoid these? And mathematically, we look at random vectors. So I write them always in bold symbols. So we have these random vectors, x, and here we have some outcomes of these, x1, x2, x3. And we would always write them in this paper as r times u, where r is the length of the random vector, so it's this, how long is this line? And then u is the distribution on the unit circle in this time, because I only printed this a two-dimensional case because it's easier to, I guess, paint a two-dimensional. So U is always like on the unit sphere, and then R is like how long is it. So now we are interested in this minimal set of riskiest directions. So we want to know where are these like riskiest directions. So a vector from the unit sphere belongs to this S, the set of the minimal set of the riskiest directions, if it fulfills this limit is 1, and then if there is some probability around it, so if it's possible that it is in this direction. So for example, if we look at this, because I think maybe this is not so intuitive what this means, I'll explain that a bit further. So if we would look at this red dot there, this is our V now. So then we would compare in the numerator, we would compare the probability, it's a conditional probability, so we only look at what is happening in this blue area, and we compare the probability, what is the probability that we have some very far away from the origin, so that R is large, it's like more than this like big circle. So we will compare what is the probability of these in comparison to all of these. And in the denominator, we would have then the probability in general that we go outside of these like big circles, so we have like large risks there. And this is very theoretical, so we look at what happens when this circle grows, so when we always go further away from the origin. But instead of comparing the probabilities straight to each other, we take this scale function, we take a logarithmic scale function because these are very small probabilities, and in order to see the difference between with dealing with these like heavy tail distributions, it's quite common to use these logarithmic scale functions. Yes. So here are all the technical assumptions. They are quite technical. I only want to say the main assumption is that this R has to be heavy-tailed for what we do in the paper. But if you're interested, you can see the other assumptions here. But now is the question, how can we find this riskiest set, the set of the riskiest directions? So we will look at this function g, which is a bit similar to what we saw. Oh, no, I went one. Yes. So it's similar to what we saw before, but now we look at the probability that R is large and U belongs to some set A, and A is part of this like unit sphere. So in two-dimensional case, it's on the circle, some set A. And what is in the denominator is exactly the same what we saw before in this formula of the set S. And actually, the denominator here is representing the whole distribution. So if we have some dominating parts, then if we go for K, letting K go bigger and bigger, then this will be what will be left. So actually, this is the most heavy part, which we get then in the end. And to get some idea how this works, let's take some examples. So if we assume that we have in general some Pareto distribution with index alpha, where alpha is larger than 1, then the tail in distribution is asymptotically same as k over, to the power of minus alpha. And now if we would have like in A this same distribution, so some Pareto distribution, then of course like this ratio will be 1. But then if we would have another Pareto distribution with a larger index, with some beta, which is larger than alpha, then the limit would not be 1 anymore, but we will get something like beta over alpha, which is larger than 1. And if we would take another distribution, for example, a Weibull distribution, which is also a heavy tail distribution, but not as heavy as Pareto distribution, then we see that the limit is infinity. So, and we use this function to find these kind of testing sets. So let's see. So we take some testing set, so which would be an open ball, or like the collection of open balls. But here we only take an open ball, and then we look at this testing set. So it's the part where the circle intersects with this set A, or like with this blue set, that's A. And we compare what is the function G for this A with what is the function G for this A complement for the rest of the set. And then if we see that there holds an inequality, it's not the same, so we know, then we can recheck this set A complement. So let's assume now we see in our example that this holds. Then we would recheck this set A complement. And if we would do the same for another set, let's say B, and we would see now the same also holds for B. So G from K and B is smaller than G from K and B complement when we go to the limit. Then we would also recheck this set B. And doing this for all kinds of testing sets, we would then in the end see that our S can be approximately found by taking the intersections. So at first we only had A, and we checked everything was around it. And in the second slide we had B, and we checked this part. So in the end what is left is only this A and B intersection. So, but in the theory we don't only use two testing sets, but more. So we take all kind of testing sets. But this is simply what this theorem here says. But let's move on to the examples. So at first we took a simulation study. So we had 800,000 two-dimensional heavy-tailed observations, and we splitted the space into 8 equally sized cones. And we assume that inside of each cone, there's the same distribution for the length of the random vector. And actually, the direction of the random vectors were equally distributed in the whole space. And we decided that 2 of these cones will have this Pareto distribution, and the other cones will have Weibull distribution. And then we tried to find this, apply this method, and try to see whether we get what we think is right. So we chose these testing sets by taking a vector and then increasing the set such that 90% of the observations lie in this set, and then we saw whether we can reject this set where it's only the 10% of the observations. And since we only have finite amount of data, we can't let go at k goes to infinity. So we had to choose at k, and this was taken such that 0.5% of the observation exceed the threshold k. And then we rejected the set if this function g from A complement was larger than the function g from A plus 1/2. So let's see what happens. So here we can see on the left side our simulated data. So you can see really like where's the more heaviest tailed. And then on the right-hand side, we can see which are the directions that are accepted. Those are the blue triangles. And then which are the rejected ones, so the red dots. So we will get this preliminary estimate for the set of the riskiest directional components, which we can see at least in the middle of each of these cones. It's quite accurate. We get the right thing. Closer to the borders, it's not so accurate because there's like close to these observations are observations which have a different tail. So after that, we since here we used like Pareto distribution and Weibull distribution, then we thought like what happens if the tails are quite similar to each other. So we used different Pareto tiles. So we had again like 8 of these cones and 2 with like Pareto distributions with index 2, and the other 6 were with like a larger tail index. But all the other parameters and how to choose testing sets were kind of same. So here on the upper line, we will have the initial data, so what we simulated. And then in the lower line, we have then the preliminary estimate. So in the first example, we had like alpha 1 was 2 and alpha 2 was 2.3. So here we didn't have enough data to reject anything. So the preliminary estimate is still the whole thing. Then for alpha 2, 2.4, we could reject a bit of it. And then we see increasing a bit this like alpha 2, we get more accurate this estimate. So it really depends on the amount of data whether we can see something or not. And in the last example, we took some real data. So we took data that was like daily changes in prices of gold and silver over a time period from 73 to 2014. And we took logarithmic differences of these daily prices to get approximately some independent and identically distributed observations. And we were only interested in the negative changes in daily prices, so when both prices declined. And the other parameters were similar as in the earlier examples. And what we got was, here we can see the real data, so now it's only in the first quadrant of the picture. And here we can see the preliminary estimate. And actually, this picture what we get here, the same example was studied in another paper, and actually the results were quite similar. So also there they got a cone. Here we got maybe 2 cones, but which was more on the upper half of these like diagonal. So yes, and to briefly conclude, so these methods can be used to identify, for example, individual components or then interactions between multiple components that produce this kind of heavy-tailedness to the total loss. But this is only a theoretical result, so in practice we only have a finite amount of data, and it might be that the largest observed data point might not be produced by the most heaviest tail, because like it might be that there's even more heavier tail, but we just didn't observe it yet. So that's our problem. And another problem is how to choose the suitable values for the parameters. So maybe we did it in the pictures, a bit like trying out and then see what nice pictures we get. But this is, I guess, a problem in all these kind of studies. So the estimator would only recover the heaviest directional components with respect to the size of the data. But there's also a few nice things about this method. So here the data does not have to be pre-processed before applying the method. And also the distance of the observations to the origin is not restricted to a specific distribution family. So there's a lot of literature about multivariate regular variation, but we don't have to have these like assumptions. It's more general in that thing. And the method also works when there are directions with only few observations or no observations at all. So we don't have to think about like, are the observations in all directions? We can just apply this method. Yes, this was it. So thank you for your attention. And here you can see the title of the paper, which is submitted to a journal. Thank you.
Okay, Miriam, our first question has come in over the network. How could you apply having identified the riskiest directional changes in gold and silver in practice? Would it be, I don't know what EG means, sorry, in risk management or trading strategies? So what, a bit more detail about how you could use the output of this for something practical.
Yes, so I think, yeah, for example, if we would get that it really depends on like one component, which is the heaviest one. So if you see, okay, it's like in our pictures, let's go to some picture maybe. Can I go? Okay, maybe not.
Can we go backward in slides?
Yes.
There we go.
Yeah. So if you would see, okay, now we would have an example where it's like we have this set is like only on this like on the y-axis. Then we see, okay, we just have to somehow have a reinsurance strategy for this like one component. If it's like some other direction, then it gets maybe a bit more complicated. But I guess the insurance companies or reinsurance companies can think about like how could you find some reinsurance products that just like handle these kind of cases. Yeah, thank you. There's a question.
Miriam, thank you very much for the presentation. My name is Florin Ginghian from Miriam in London. I was thinking about my question, and then I processed it to make it, more friendly. The question is, for example, in hedging strategies, it's quite often that, to give an example, a life insurer might be worried about inflation going up and exchange rates going in the wrong direction at the same time. In this setting, then, looking at your presentation, I think that's very applicable. What happens sometimes in real life is that people put expert judgment into these sort of calculations. And the question really is, expert judgment meaning policy, interventions from the government, like we have seen with inflation, to keep it low or to limit its growth. So the question is, how adaptable is the framework that you described in your paper to manual interventions? Like I want to put some restrictions, limits, or just truncated distributions even.
Can you repeat the last part of your questions? I didn't really hear.
Sorry? You didn't understand the question?
Yeah, just say the last part of the question.
Oh, truncated distributions, for example, or truncated, I don't know.
Okay. I didn't really look at that part, so I'm not sure how to handle these situations. But I guess it's a good idea for further research.
Thank you for the presentation. There were so many equations, but very interesting presentation. So sounds like this area is evolving, showing that the theory, the theorem was 2023, which is just came out. But just wondering, maybe you just covered in the first part of the presentation, but what about the univariate version? Is that because you are dealing with some complex thing, but on the univariate version, is that really known, or is another different thing?
Yeah, so if we have a univariate case, then we are not, the direction is clear. So here we just look, if we have multivariate models, then it might be that there's some things we don't have to think about, for example, some reinsurance strategies for some lines of business because they are not heavy-tailed, but then there might be some which are these heavy-tailed. So I think this problem arises only when you look at multivariate cases.
So in that case, say, if dimension is 2, finding direction is easier among multivariate?
So finding, I think, in all higher dimensions, I think this is a quite important question, to find the directions, because, because then you don't, have to find a hedging strategy which like covers all directions, but maybe you can like break down your problem and say, okay, we have some things that we don't need to like ensure that like this won't be very big because it's not going to be big, but then we have like some other lines of business which might like have these like larger outcomes. So then we just need like some reinsurance strategy for these parts of the company. But then maybe a more general, like maybe some companies also like look at like one line of business at the same time. So maybe they don't take into consideration like what happens like if two lines of business have like this super large outcome at the same time. So that's why we look at the whole company, or like we have this multivariate thing. Because yeah, if you have this, like, if you only look at univariate, and then you can say, okay, we have this risk here, and we also have it in another model which is univariate, but it might be that they have some kind of dependence. So it might be if there is like a earthquake somewhere, then like it affects two lines of business instead of just one. So.
Thank you.
Thank you.
While we're waiting for another question, I have one for you. I noticed you used a simulation approach towards the end. Does that mean that this approach could be used on the output from a stochastic capital model with simulation model?
I guess you can at least try it and see whether you get something reasonable out of it. So, yeah, so we wanted to see with the simulation study if like we know what the observations look like in this one part, then like whether this method works and whether it shows this what we think it should show. So.
This is the quietest I've seen a room. And at least it means what you're saying is not controversial. We'd have lots of people queuing up to disagree with you. In the lack of questions, we might move on to the next speaker then. Thank you very much again, Miriam.